The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi, I'm Sal. Today we're going to solve problem 8 of the final exam of 2009 for 3091. The problem reads as follows. The phospholipid, the chemical formula is right here, is added to hexane, which is C6H14, which is a hydrocarbon, in sufficient quantities to enable interaction between phospholipid molecules. Draw a cartoon depicting one possible molecular arrangement that results. You may stylize your parts of the phospholipid molecule as, with the squiggly line, which is shown in the exam, for a hydrocarbon chain. So if we look at our molecule here, the first thing that we want to understand is what the structure is. And as you can see, the molecule has a nonpolar component and it has a polar component. So for the problem, it will be good to we'll isolate the two with different colors, and then we'll stylize them such that the hydrocarbon is just a zigzag line, or the nonpolar part is a zigzag line, and the polar component is the red circle. So we want to go ahead and draw the arrangement together when it's added to hexane. So the first thing to do, or the easiest thing to do, is to draw a picture. So if we come over here to the right, this is part A. I'm going to draw a beaker with hexane. And I know that as soon as I look at my chemical formula for hexane, which is C6H14, and it's a hydrocarbon, I know that it's nonpolar. So I know from my knowledge of 3091 and chemical bonding that like dissolves like. So the molecules that are polar are going to want to stick together, and molecules that are nonpolar are going to want to stick together. So by looking at my phospholipid, I already know that the problem tells me that I'm adding a sufficient amount such that the molecules can interact with each other. So the only thing that comes to mind for me that will be a possible arrangement would be that in the hexane, which is nonpolar, and if we have a distribution of these phospholipid molecules, then one possible arrangement will be that you have a bunch of your polar heads interacting together with the hydrocarbon components out here interacting with the hexane, because the hydrocarbon component, again, is nonpolar, the hexane is nonpolar, so those want to interact with each other. But the polar component, which are the heads for the molecule, the phospholipid molecule, are going to go ahead and interact with each other. And pretty much if you were to write this down on the exam, you would get full points for part A. Now we'll move on to part B. Part B says, to the beaker described in part A, an equal volume of liquid ammonia, NH3, is added. The mixture of hexane NH3 or ammonia containing the phospholipid is then subjected to vigorous agitation for several minutes and then allowed to equilibrate. Draw a schematic representation depicting one possible molecular arrangement that results. The values of density are 0.65 grams per centimeter for hexane and 0.6 grams centimeter cube for liquid ammonia. Assume the hexane and liquid ammonia are mutually immiscible. So there's a lot of information within the paragraph. And the first thing that it gives us is the densities between the two components. It tells us they're immiscible, so immiscibility means that they're not going to mix, which is then going to be the question that you want to answer now is that which layer is going to be at the top, which layer is going to be at the bottom. Well, the more dense layer should be at the bottom, and the more dense happens to be hexane. So if I go ahead and draw my beaker again for part B, I mix my components, so now I have two components that are separated by an immiscible boundary. And I know that the density of hexane is given by 0.65 grams per centimeter cube. And the density of liquid ammonia, which is NH3, is given as 0.60 grams per centimeter cube. So I know that the hexane is going to be down here, so I'll go ahead and label this C6H14, and I'll label this as NH3. So one important thing to know is, what is the structure of ammonia? Well, we know that ammonia happens to be a polar molecule, and its structure is simply given by, you have a central nitrogen atom, and you have 3 hydrogens and a lone pair of electrons. And the lone pair of electrons is what gives the ammonia the structure. Hence, you have a net polar dipole moment on your molecule. The fact that this is polar means that it's going to interact with the polar head of your phospholipid molecule. And since we already know we have this is hexane plus your phospholipid, well, if in our arrangement, in the absence of ammonia, the heads grouped together because that was the only polar component in the mixture, then over here I should expect the heads to rearrange themselves such that they are in contact with the ammonia. So one possible arrangement for this system would be that I would have my polar part of my molecule interacting with the ammonia, and the hydrocarbon chain interacting, which is the nonpolar component, interacting with the nonpolar mixture. So if you were to draw this schematic, then you would get full points on the exam as well. So that's, again, like dissolves like, and if you fully understand what the nature of secondary bonding, then this problem shouldn't be that difficult to go through. Now, there's a final part to this problem, which is part C. And part C says, to the beaker described in part B, a small amount of iodine, I2, is added to the mixture and then subjected to vigorous agitation for several minutes, and then allowed to equilibrate. Explain what you expect to observe. Again, we're going on this whole issue of like dissolves like, or that polar components or polar molecules want to be with polar molecules because they should be miscible together. And we are given that now we're going to add I2, iodine. Well, iodine is a linear molecule that's nonpolar. There's no other atoms that are bonded to it that can give any polarity. So if I was to go ahead and draw this diagram, the first thing that comes to my mind is that the iodine should mix with the hexane, because essentially it's a nonpolar component mixing with another nonpolar component. So if I draw my diagram, I'm going to go ahead and label, draw the two immiscible regions. And one question that a lot of students have is, well, how do you know that the iodine is not going to be on top of the ammonia? Well, iodine is pretty dense. It's actually more dense than these two molecules over here. So the fact that it's more dense, I know it's going to want to sit at the bottom where the other nonpolar molecule is at. So I would argue that down here we would have hexane, C6H14, mixed with iodine. Over here we would still have our ammonia, and then our polar heads would still be, the polar part of the phospholipid molecule will be in contact or bonding with the ammonia, and the nonpolar tail would be with the nonpolar components, which is hexane and iodine. So if you did this on the exam, you get full points, and being able to fully understand secondary bonding will help you solve this problem in no less than 10 minutes. So that's it.